Welcome to Stay Sharp in Digital Engineering, the podcast that sharpens your understanding of digital innovation for products and manufacturing. Jonathan Scott and I welcome back David Long, an MBSE expert and an INCOSE leader, to help us take a look at the evolution of MBSE to better understand where it's going. We discuss how these models emerged, the need for convergence across engineering disciplines, and how organizational structure shapes the ultimate success. Let's listen in. Hey, everybody. Welcome back to Stay Sharp in Digital Engineering, the podcast about all things digital related to products, engineering, manufacturing, service, and more. I'm one of your hosts, Julianne Grant, and I'm joined today by my co-host, Jonathan Scott.
Hello, everybody.
Hey, Jonathan. Always good to be here with you.
Yeah, no, I'm excited. I love doing these. This is always a fun part of the week, but I'm super excited about today's episode.
Yes, and so am I. Today, we're here to talk about model-based systems engineering and dig in deeper to the landscape of model-based systems engineering. Now, we've talked about MBSE in other episodes. We've talked about it from a digital twin perspective. We've talked about it in the value of organizations. But today, we have back an expert, and we're excited to have him back, who can help us talk a little bit more about the history and the whole scope of model-based systems engineering, because he's built his career in this space. And so we wanted to really get a chance to pick his brain. Well, I'll be honest, Jonathan really wants to pick his brain.
It's true.
About this topic in general. So this will be a good primer for anyone who doesn't really know a lot about MBSE and just kind of wants to get the background of how all this discipline came together. So we're happy to have David Long back with us today. Welcome, David.
Great to be back.
Yeah, we're glad to have you. So for those of you who missed the last episode, David helped us with a conversation around model-based systems engineering and the digital twin and where that all fits. So be sure to go check that podcast out. But I'll just give you a brief overview in his bio. So David spent more than 30 years helping organizations around the world increase their systems engineering proficiency, particularly in the areas of model-based systems engineering and digital engineering. So David founded and led Vitech, where he developed innovative industry-leading methods and software that helped organizations engineer next-generation systems. He's also an INCOSE Fellow and expert systems engineering professional. David was the 2014-2015 president of INCOSE and currently serves as INCOSE's Director for Strategic Integration. So we're really glad to have you here, David.
Great.
Yeah, thanks for being here, because this is, for the topic we want to dig into, I really can't think of a better person to answer these questions and get into this stuff. So with that,
I expect another fun dialogue, Jonathan.
Absolutely. So with that, I'm going to get going because I've got lots of them. So in the past, when we get into episodes, we make it a point to define what it is we're talking about. I don't think we need to do that today before we launch in, though, because when we get into this first question, I think it's going to sort of explain itself. I think it's going to set the stage too. So let me head right there. What's the background and history of MBSE? I mean, we all know that because of the definition, right? MBSE, it comes from system engineering.
Right.
But why do we need a separate thing for model-based systems engineering, and what drove this? Where did it come from?
Sure. So I love the way that you frame this, because it's an evolution of how we do systems engineering rather than a different thing. And it's enabled, obviously, by digital. But why? Why do we bother? Well, it all stems from the growth in complexity. When we were dealing with electromechanical technologies, and that's where the primary functionality, the primary value add in systems came about, the implementation technology, well, the mental models that we had and capturing those in documents was sufficient. When you got into the 80s and particularly the 1990s, and you saw the rise of what were termed software-centric systems, so in other words, or software-intensive systems, the majority of capability was coming out of cyber. If you think about the interconnectedness of cyber systems, they are much higher than electromechanical. The complexity goes way up. And so we were noticing not only was there a rise in the role of cyber, the importance of cyber, but we were noticing a breakdown in dialogue between systems engineers and software engineers. We were not able to effectively communicate. And so while there was a rise of computer-aided systems engineering tools in the late 80s and early 90s, what we currently call model-based systems engineering today arose out of that communication mismatch. And so put simply, what are we trying to do today? We're trying to better capture that knowledge, better communicate that knowledge, better analyze to deliver these more complex systems across a diverse team. And it was the system software mismatch that started it all.
Well, that's interesting. I'm not a student of that history, so I appreciate you sharing sort of that, evolution with us, like you said. So, but you mentioned case tools, right? Case tools of the 80s and 90s, and that we were struggling a little bit with all the communication. Is part of it that, case tools helped us on the computer side, but as systems engineers, the point is overall architecture. So we're still leaving out electromechanical. So MBSE becomes that evolution of let's put it all together, right? Is that part of it too?
It's part of it, Jonathan. But if you go back to the 80s and 90s, there were some very powerful tools that enabled full comprehensive architecture, both software and physical. The issue was systems engineers had their language and their concepts and their visualizations. So it's not only a matter of systems engineers had the ideas that were most important to them, their concerns, but they had a specific way of communicating them. We learned over the years how to do that translation from system to electro, system to mechanical engineer and talk effectively. Software engineers, it's interesting because the language of software is very, very close to the language of systems. It makes sense. What are they interested in? They're interested in architecture and implementation and all those ideas. But their language and notation is slightly different. And it was that mismatch, the mismatch in notation, the mismatch in terminology, that said we're not communicating effectively. And in fact, what we currently call MBSE emerged in 2003 to 2006, specifically trying to align notations under the belief that if we will align notation, we will more effectively communicate between big systems engineering architecture and software architecture and detailed implementation as the key driver in capabilities in modern systems.
Okay. So does that, I'm connecting a lot of dots with what you're saying. Sure. Does that explain why SysML v1 came out of UML? I mean, is that part of that connection? Okay.
That's exactly right, Jonathan. And so if you look back to the late 90s, early 2000s, and you say, if I'm going to try to close that communication gap, there are a lot more software engineers than systems engineers. How do software engineers formalize their communication? Well, we were looking at the very early days of UML as a standardized visualization, a standardized notation for capturing software concepts, software architectures. It was very natural, therefore, for the systems engineers to go, well, let's adopt that language in large part, but there are aspects that don't speak to us. We'll ignore those. There are aspects that we need to add. We'll add those. And that's how SysML, the systems modeling language, became formalized as a profile on top of UML, the unified modeling language.
Cool. Well, this connects a lot of dots, right? I mean, it makes sense why all these things kind of fit the way that they do. You mentioned something else in our conversation related to MBSE, and I think maybe it's not that you mentioned it directly, but I interpreted when we talk about descriptive languages and descriptive models, and then the visualizations we use and all those things. And it reminds me of something that has occurred to me in my sort of relatively novice MBSE journey. And that is about how model-based systems engineering feels like it is democratizing systems engineering to more engineering disciplines, right? Because what was in systems engineering, a lot of implicit models that experts and people formally trained knew how to make those mental models. Now you can actually show them to people who are not systems engineers, have them understand them and learn and that sort of thing. And so in this history, this evolution, what it brings me to, it actually brings me to a question is, are we seeing that democratization across industries as well, right? I know aerospace and defense is making tremendous use out of MBSE, but of course, they've always been tremendous users of systems engineering in the first place. is MBSE helping us apply systems engineering out to other industries? Do you see that?
It absolutely is. And so you're correct by, I'm going to say formalizing, but be careful of that word because that can imply raising the barrier of entry. But by structuring and adopting a common, let's call it a concept map or language that allows us to encode what is systems engineering all about? How do we capture the problem space? How do we capture the solution space? We have lowered the barrier of entry, and we've allowed other fields, other application domains to look at it and say, you know what? I never would have called it systems engineering, but we've been doing that for a long, long time.
Yep.
And so it's not that all goodness flows from any one application domain, certainly not aerospace and defense, but MBSE has allowed us to connect practices in automotive, in transport, in medical device, in energy design, basically anybody who's dealing with building and managing a complex system. They had developed similar ways of working. And because we can now better express that old implicit concept map in an explicit way, we're able to connect learnings across disciplines. And we've seen great adoption across disciplines. Across application domains.
Yeah, that so many things you're talking about there resonate with me, right? And not to bring my own journey into this too much, but that point about democratization and recognition of certain practices as just being something systems engineers already do, and maybe they bring something to the table. I think this is great. To me, those intersections of domains is an amazing thing about moving us forward in terms of overall progress. I'll give an example. I, for years, struggled with this concept of requirements decomposition, right? I knew it was needed. I did it in engineering work as a mechanical engineer, and that's my background. But I never really understood fundamentally how you're supposed to do it in a structured way. Being introduced to MBSE tools and seeing like, oh, okay, you do this, this is how it works, this is how that connects, you apply this here. Suddenly it was like, aha, what I needed was an example, and making those explicit is what helps do that. And it really just helps us all communicate better, to your point.
Well, and Jonathan, what you call out there now, I am going to use formalism in the other sense of the word, which is there's often an analogy drawn that says, if you want to understand what MBSE is, go back and look at the evolution of mechanical design from drafting to CAD. Mm-hmm. And so MBSE is CAD for systems engineers. Good analogy.
I love that.
That's interesting.
It's a good analogy, but you got to take it one step further, because you have to realize that we've been doing mechanical engineering for centuries, if not millennia. Systems engineering is relatively new, which means we don't have the formalized body of knowledge underlying systems engineering. That's why it was hard for you to understand, how do I derive requirements? What does requirements flow down really mean? What does an allocation really mean? As long as you're dealing with mental models captured in documents, implicit knowledge, you can be a little sloppy. Mm-hmm. When you're dealing with digital, you've got to be more precise. And so part of this journey to MBSE that's missing from CAD, because they already had their formalisms, the journey to MBSE is forcing systems engineering to clarify and define its formalisms, which I think in the process demystifies it and again democratizes it.
I love it. And the thing that you said a minute ago absolutely resonates with me, that MBSE is CAD for systems engineers.
Yep.
Right? That analogy I think is very useful. Yeah, I can't say I love that one enough.
Good.
It's a great transition though to something I think we should talk about.
Should make a meme out of that.
We should. Oh, now that gets us back to AI. Now I got to go back to an AI and say, make me a meme. But it brings me to what I think is the next logical question in that history is, okay, so if MBSE really is rooted in sort of the tools, the digital tools, how did those come about, right? How did we get those? Who started that? who are some of those early leaders in developing the tools, and kind of who's in that space today? Can you kind of give us that sort of overview?
Sure. So there are probably 4 groups worth talking about, or 4 classes, because there are 4 different derivation stories.
Okay.
The market leader today is absolutely, it was originally known as Magic Draw from No Magic. It was acquired by Dassault, so it's known as, many people know it as Magic Draw, some as Cameo, now CATIA Systems Magic. But that is a generation of tools that came directly out of that MBSE origin story that I told of, let's close the gap with software. So they built on top of a UML foundation. They were right there helping to drive the original standards. And so they have continued their systems engineering working from that point. There are a few other tools that fall in that general category, but that is the dominant tool to talk about. Okay. The next class of tools that I would talk about would be those that really focus on the visualizations.
Okay.
Because what's the primary visual that comes out of model-based systems engineering? It's all these diagrams.
Right.
And there's a whole host of different diagrams that exist either from systems engineering or architecture. So you have tools such as enterprise architecture by Sparx these days. Okay. So if you go back to Dassault, it's about connected engineering building on top of software. If you go to Sparx, it's about quick visualization and communication.
Okay.
Not necessarily analysis, it's communication. The third class of tools probably date back longer, not necessarily as dominant right now, and it would be the Vitek history that I have with now Vitek, Zook, and Genesis. It would be Capella, which is an open source tool that came out of Thales as an organization. It would be InnoSlate, which comes out of Spec Innovation. And those tools are ones that I would call by systems engineers for systems engineers.
Okay.
So they didn't emerge from the software heritage. They emerged from really computer-aided systems engineering, and then they've tried to adapt into modern model-based. The fourth class of tools is just now coming online. And that is, as model-based hits this next leg of its evolution, that disruption creates an innovation space. And so we see new organizations coming on board with systems tools, new startups. But we also see organizations such as ANSYS and MathWorks, who have high-fidelity engineering tools, say, let me move into the system space and produce an architecture tool that can connect my engineering lifecycle or the engineering lifecycle of my customers. So those are probably 4 categories and a number of the major tools in each.
That's really interesting. I didn't have any sense of that subdivision, excuse me, of the MBSE space. And that last one is really interesting because I've certainly seen that, right? When I look around at vendors, I've seen, ANSYS and other people saying, hey, this is a logical extension of the portfolio of what we do.
Yes.
But that's an interesting as a separate category. Okay, that's really cool, that sort of breakdown. Let's keep going on players, though. What about people, organizations, other things we should know in this space if we're trying to get a handle on MBSE?
Sure. So if you're looking for the big names in this space, it's going to start with Sandy Friedenthal and Ed Seidowitz, who are the drivers behind the SysML standards. Okay. There are going to be leading thinkers and trainers, people like Lenny Delegati, Tim Velkins. So as your organization is seeking to understand and deploy, you can pick up their textbooks. You can attend their classes. Organizationally, certainly the driver of standards here is OMG, the Object Management Group. They created what I call the technical stack in this space. UML at the software level, SysML at the system level, originally V1, soon to release V2. And then on top of that stack, UAF, Unified Architecture Framework for the enterprise level. And so that creates an integrated vertical stack from enterprise through system to software, specification-wise. So if you want to know that space, it's Object Management Group. And then we are still talking about systems engineering. And so I would include INCOSE, the International Council on Systems Engineering there, as the world-leading professional body for systems engineers and the discipline and practice of systems engineering. Those are probably the big individuals, standards players, and organizations I'll consider.
That's great, and I'm proud to say I've recognized a few of them. It's in my own journey in learning MBSE and systems engineering, I can't say enough about Incosi. You mentioned them, that just in terms of a resource to know where to find the other information. And of course, that's the case a lot of times, right? Standards bodies really can provide that, but organizations that are alive and well, and groups of professionals, that's just a super helpful resource.
It's a great comment, Jonathan, and two things there. One is, if you're taking any journey, a community of practice is essential, because you need people who can share what's worked, what hasn't, places that you can talk. And Incosi is that home for systems engineering. The other thing I'll call out here, though, is in the journey to model-based systems engineering, there are people who get off track, and it comes out of the name itself. It is very easy, particularly technologists, particularly engineers, to fall in love with the model-based part of the title. After all, that's what's new. That's what's sexy. That's what allows us to do more than we used to do. But that's falling in love with tool and technology. And the individuals who do that often will apply a lot of effort without necessarily the business outcome that's valuable. In the phrase MBSE, I like to put parentheses around the MB because it's the enabler, and underline the SE. If you're not doing good systems engineering, if you're not understanding what systems engineering is trying to do, doing it faster, doing it better, it doesn't matter.
Yeah.
And so Incosi is the organization that helps you on the SE. It has an MB flavor in it. OMG brings the standards, the tool vendors bring the enabling software.
It reminds me of the thing I've seen people fall into this pitfall as well, and I've worked with customers on this. You get into a conversation like, yeah, we're using systems engineering on this project. We're laying out the architecture, that sort of thing. And you get into it and you're like, all right, yeah, share the model. Let me look at it. And you figure out very quickly that they've paid a lot of money for a very capable systems engineering tool that they use to make pictures.
It's the story of any technological evolution, right?
Right.
You can use the tool and not understand the principles. If you know the principles, the tool's a tremendous enabler. The way I like to say it is, the tool handles the perspiration, freeing the engineer for the inspiration.
Yeah.
That's fair. I think that you can see where AI would come in on the MB part, right? To help kind of maybe accelerate and not make that as sexy but make it something very easy to do or easier to do. So they don't spend as much time on, creating these models, really just focusing more on the discipline of systems engineering. So,
well, and the other thing, Julianne, thanks for bringing AI into the conversation. If we think about what AI is doing with large language models, it's trying to understand and predict and extend based upon that. Well, what's MBSE doing? MBSE is trying to represent the knowledge map for systems in a higher fidelity way. That therefore is very complementary and synergistic. Turn AI loose on structured knowledge about systems, particularly your organization's systems, and we can imagine next level capability inside of our organizations.
Yeah, interesting. Well, so that brings to my next question is, so AI is always a topic in pretty much any conversation we're having these days. So Are there other big topics happening in model-based systems engineering right now?
There are probably two other topics, and I think they're kind of global topics in the digital transformation of engineering. First is cloud. Jonathan, you talked about democratization. Democratization is about access to knowledge, access to capabilities. And as long as these tools are locked up on desktops, then that's a limiter for the enterprise. It's a limiter for the collaborating enterprises. So cloud is a big part of it as these organizations go to make their knowledge more accessible, their capability more accessible. The other thing is MBSE, as positive as it has been inward looking for systems engineers. It's how do we do our job better through the application of digital and the application of technology. Well, systems engineering was never meant to look inward. It was meant to look outward. And so the next piece for us is looking at digital engineering, which for me is the transformation of the engineering lifecycle, the transformation of the engineering enterprise, and therefore, how do good modern MBSE practices enable that end-to-end capability to transform need into business value?
That's deep.
Well, I'm thinking in my mind, like, that's a big door opener for Jonathan. I mean, we're treading on PLM territory, and
well, it makes perfect sense though, right? And I see it. The reason I say it's deep is like suddenly my mind's turning. I'm like, well, normally I've got a quick
explode a little bit.
Yeah.
So Jonathan, let me bridge it for you a little bit. And this is where you can get into religious wars. I don't think religious wars are particularly helpful, particularly in technology.
Right.
But it's two different ways of viewing the world. PLM says the center of all knowledge for the engineering lifecycle is effectively the BOM, right?
Right.
If you asked a systems engineer, they would say the integrating technical connective tissue for the engineering lifecycle is the architecture.
Mm-hmm.
Now, I don't know which is right and which is wrong. And the answer is they're probably both right. It may be that the architecture in the early engineering phases is what binds us together. And that's represented now in an MBSE knowledge map. As it begins to mature and firm up, then it's probably in the BOM and PLM. But that thought process that the architecture does not exist to serve the systems engineer, but the architecture exists to serve the engineering enterprise is the critical mindset so that systems engineers are deploying MBSE, enterprises are deploying MBSE in a way that serves the engineering lifecycle rather than creating a new silo.
Well, and I think that to me, it does align in there. We shouldn't have a religious war about it because it feels like that's where a lot of engineering was headed anyway. So I see the two connecting in the middle very well because so many PLM, I'll say mature PLM organizations, we're starting to ask the question, hey, I've got my bill of material under control. I've got my implementation specifications under control. Whether it's electrical, mechanical, software, whatever it is. And I'm looking downstream and that kind of thing. So they were getting a good PLM picture, but they said, something's missing. What's missing is, can I connect it back to the requirements and the needs so that when I make a change, when I analyze something in the life cycle, do I understand why? Right? And that gets right back to that architecture point, which is systems engineers have been looking at it from that perspective the whole time. Hey, wait, if we connect the requirements and the needs to the architecture, then anytime we need to analyze and evaluate something, we've got the basis right there for making the decision. So to me, it's like they've been figuring out the same answer, and now suddenly they've got a language to come together on.
Yeah, you're exactly right. And they've been coming at it from the two different sides. They've been coming at it from downstream, upstream, if you want to call it that. And it serves us both in the engineering of the current product and in the engineering of the next block upgrade, the next generation. Because, okay, you may not make that change now, but then if you can feed this high fidelity end-to-end representation of your product into the next generation product lifecycle, wow, you want to talk about knowledge management, knowledge retention, and an accelerator for the engineering enterprise. If you don't have to recreate all this knowledge, implicit knowledge that walks out the door every night at 5, you can do radically different things.
So I've got to jump in here because when Julianne asked the question, I was expecting an answer that I didn't hear. So I got to follow up and ask about it. And maybe there's a good reason why it doesn't fit. Biggest topics in the industry, why not SysML v2? Why would that not be on your list?
It should have been, and thanks for calling that out. SysML v2 is the next generation. It takes all the learnings that we've had from 18 years of application of SysML v1, and it completely re-architects it in two ways. One is it looks at it and says, originally we were built on UML. Where, yes, we tried to add some formalisms and whatnot, but UML really was initially a sketching language. So there's only so much knowledge strength in UML, therefore only so much reasoning that you could put in SysML. We need more. And so SysML v2 puts it on a formal basis, which allows us to more rigorously connect engineering, really high value. The other thing SysML v2 does is it looks not only inward at systems engineering, but outward at how do we make that knowledge available to non-systems engineers, to other engineering tools through standardized approaches. So yeah, Jonathan, v2 is this enabler at a technology level that underpins the journey to AI, the journey to digital thread, the journey to digital engineering. And so it is probably the biggest dialogue point in model-based systems engineering these days.
Okay, good. I'm glad to hear it's as important as I've heard it was in other contexts, right? One of the pieces that I've heard is about interoperability today, and I know we struggle with this, is MBSE models being, shareable across software platforms, tools, that kind of thing. And that SysML v2 is hopefully going to help us in that space too.
Exactly right. And it's a combination of that underlying formalism so that we're all speaking to the same concept map, that we're developing compatible knowledge maps, so to speak. But then that's great. You still have to have a standardized way of accessing that knowledge. And a critical point in V2 has been a standard set of APIs and services to unlock the knowledge beyond the systems engineers, beyond the so-called authoring tools and the creators, so that we can connect this through life.
And that gets us back to the point we were discussing a second ago, right? About like the PLM view of the world, the MBSE view of the world. Hey, if we could bring that together, great. That's, everybody wins. So that's awesome that's sort of part of what we're trying to do there.
Yeah, absolutely. And it's not about tearing down those silos. It's about connecting them. You got it spot on, Jonathan.
So quick question on the SysML v2. So, typically when they move from one thing to another, or a new language to an older language to a new language, there's usually some hurdles. Do you anticipate any big hurdles here, or do you think that's going to be a fairly easy transition?
There are big hurdles indeed. So if you look at it from the vendor community has been working on this for probably 2+ years in terms of implementing new versions of their tools. Some of them are out. The standard here releases shortly, but we're going to watch tools deploy over the next 18 to 24 months because the scope of SysML v2 is huge. Okay, they've not just taken the previous scope and put it on a formal basis and put an API around it. They've expanded the scope to do more. So that is complicated. And the other thing is they've moved off of UML as a foundation, and they've put a formal foundation under it called kernel, the kernel modeling language. But what matters is that it's a formalism. To go from somewhat soft semantics in V1X to very, very firm semantics in V2, that's a leap for the practitioner. It's a transform for the knowledge. It's not going to be a lossless conversion. And so organizations will need to be thoughtful to say, hey, where am I in my engineering lifecycle? Should I bother transitioning now on this engineering project, or do I see this one through in V1? Do I start something new in V2? When am I starting it? Are my tools mature enough? Can I train my workforce? And then if models represent kind of knowledge repositories, what models do I need to invest in transforming because I'm going to use them over and over and over again in the future? Which should I keep in their current form because they're really legacy knowledge? So it's going to require thoughtful investment. It is going to be investment, but it's investment with high return.
It's amazing to me. Everything you just said so perfectly mirrors the CAD migration story, right? And so that analogy we talked about earlier, it keeps fitting perfectly. When I go from drafting to 2D CAD or from 2D CAD to 3D CAD, what do I move across? What do I keep? What do I migrate? What do I just hold on to as legacy? All those things. It's the same thing. That's fascinating.
There you go. So let's be informed by our past.
Yeah.
Perfect, Jonathan.
Yes. And so I know we're going to have to move into our summary discussions because we are certainly a little over time. But I just want to have a quick question for one more thing to mention for David. So I imagine in Cozy will have some classes or training around SysML 1 to SysML 2, I'm assuming, or there'll be some resources.
In Cozy is trying to figure out their role in the training ecosystem.
Okay.
I will say that people like Lenny Delgatti, Tim Velkins, and other providers will have classes. What Cozy is doing is Cozy is working with the stakeholder community, people like the U.S. Department of Defense and others, to map out what transformation looks like. And then training bodies can take that information and put it into courseware.
All right. This will be a very interesting conversation. So
yes. This has been awesome.
Yeah, there aren't too many people who make Jonathan a little speechless. So I have to give it to you, David. You did
it. You're winning on that front.
Yes, you are. So Jonathan, what do we got for a summary?
I got lots.
Okay.
This has been a great conversation, sort of roaming around that landscape, right? Because there's a lot to cover. So here are the key points that I took away, and I know I missed some. But I'm going to start with the history, right? So MBSE came about because we were struggling with some things as technology evolved in other areas, right? So we had systems engineering back in the day because of electromechanical and complexities in multiple domains and disciplines. But MBSE said, hey, as we're moving to that next step and computers and software come into it, we need something more, right? So it's a logical evolution, and we can see it sort of mapped with the history of systems engineering. So that's one big one in terms of how we got here. I won't talk as much about, I think, the definition, but we did cover that some too, which is important, making sure that that's still clear for people. The one analogy I love as we were talking about that, though, is the parallel we drew between MBSE and CAD. Like MBSE is the CAD for systems engineering. And I think that's such a great analogy, and we touched on it here at the end of the conversation too, as we think about how it evolves from SysML v1 to SysML v2, and what do you do with that information, that knowledge, as you carry it forward, as we get better and better models, right? And even models coming from our traditional systems engineering documents. So all of that, there's just a parallel. So if you've got a background in mechanical, electrical CAD, and you're thinking, how does that apply? There's a clear application here that you can learn about as we move forward in MBSE. So a couple other things. In the landscape overall, we've got a number of interesting names that David mentioned, people who are kind of leaders that you might want to follow, check out, see what they're up to. Organizations as well, some of the different software vendors, and we kind of put the softwares into about 4 categories. Again, I won't recap all of that, but I think that's very interesting for the landscape as people are thinking about tools or what they might do to apply some of these concepts. And then I think the last big one that I took away was about the 2 different perspectives, the systems engineering and MBSE perspective on architecture leading and the current sort of PLM perspective on digital engineering and the product structure leading, and how we need to put those together. They're probably logically coming together anyway, but that's really going to help us with this transformation into digital engineering and overall digital transformation for product-centric companies. So last thing I'll mention, SysML v2, it's a big deal. It's a thing that people are paying attention to. It's one of the hot topics right now. I think that's the net of what we talked about, but I know I missed some stuff. David, what did I miss?
Jonathan, you did a great job pulling those nuggets and those key points out of a 30-minute conversation. I think you captured them all beautifully. The one thing that I would augment, and you touched upon it when you talked about the analogy of CAD, when we used it in the beginning and then brought it back at the end. And that is the recognition that we're on a continuous journey. Mm-hmm. And as you said, even when you talked about going from the systems view of the world to the PLM view of the world, they really should connect, and we're on that kind of journey. We also need to recognize, drafting to CAD, systems engineering to MBSE, but whatever lies beyond, it is going to be a continuous evolution. And if we adopt that evolution mindset, as you were starting to frame, that's going to serve us individually, collectively, and organizationally well. Great synopsis, Jonathan.
Thank you.
Great. Awesome. Yeah, you could just really see a big convergence coming together of all the disciplines, which is needed. I think nothing operates in and of itself anymore. So, Okay. Well, thank you so much, David. This has been a very
Absolutely.
great, very interesting conversation. So we appreciate your time today.
This has
Truly
been great.
pleasure.
Yeah.
This has really been great.
Yeah, I'm sure there'll be plenty of nuggets that people get when they listen to this podcast. We'll also add some notes in on our YouTube page for some of these links to the people and the folks and the software that was mentioned today. So if you want to find those links, we'll have them for you. With that, we thank you for your time. We're grateful that you're listening in with us. And if you have any questions for David as well, please send us a note or make a comment on our post and give a like to this post if you enjoyed the podcast. And with that, we appreciate everyone's time today and make sure to tune into future episodes. And we'll probably have David back, hopefully, another time later on. And we'd love to have that. And with that, everybody, stay sharp.
Thanks, everybody.
Thanks all.
Thanks for being here and listening to this episode of Stay Sharp with Razor Leaf. If you liked our podcast, please be sure to hit the like button and subscribe to our podcast on your favorite podcast platform. Or check us out in video on our YouTube channel. If you have any questions for David, Long, or for us, please leave us a comment on our post or send us an email to podcast@razorleaf.com. Until next time, everybody, stay sharp.